Okay, today we're going to talk about or introduce a derivative, and we're not going to get too far into what a derivative, what it all entails, but we are definitely going to get into the what I would call an introductory definition to a derivative, and that is the study of rates of change, and specifically an instantaneous rate of change versus an average rate of change. And some of you are going to start to really make some connections over the next couple weeks. Between your physics class and your calc class, and you're going to realize all the great stuff you get to do as in physics. You might as well be thanking all the mathematicians because they are the ones that gave you all the shortcuts you guys have. Now, I will say this about the physicists: it's usually the physicists that prompt the need for a lot of the shortcuts. So the physicists actually do a lot of the discovery and trying things, and even Sir Isaac Newton, he was a physicist and a mathematician, and he contemplated things from the physics side of things and thought about why things work and trying to figure out why this works and why this doesn't work and how can I figure something out that relates to this. And then he came back at it through the mathematical point of view and actually proved how you can work these things out quickly with shortcuts and mathematical variations. So instantaneous rate of change today versus average rate of change. Now, when I say average, most of you get a pretty good feel for what an average is, right? Okay, most of you know what an average is. I'm not going to have too much stress over what an average rate of change is. But what we need to do is we need to change your definition of an average rate of change today. The first time you're introduced what an average rate of change is in ninth grade when you talk about ninth grade slope. Because slope is really referred to as average rate of change. Okay, that's what the big idea in ninth grade is trying to get you to understand that slope is really an average rate of change. So what I'm going to have you do is I'm going to have you draw pictures today, and we're going to do a proof of what you did in ninth grade. I have two definitions for average rate of change. I have this definition right here, which is kind of funky looking, and I want to prove that this definition here is no different than your ninth grade definition of slope. So let me go through the ninth grade definition of slope first. Average rate of change, which is also referred to as the slope of the secant line, or also called the difference quotient, is defined as this crazy looking formula right here. Now the reason we're going to like this formula better in calculus is because it determines slope. It determines slope between 2 points, but it doesn't matter what those 2 points are. See, in ninth grade, you had to have a specific, you needed to know 2 specific points. You needed to specifically know, hey, I got this point and I have this point, now I can calculate slope. This doesn't matter. This will calculate it based on any x value that you have. You can move the x values around all you want, okay? Because this is calculating slope based on any x value. Where this specifically calculates slope off of 2 x values. Let me explain this one. The average rate of change, let me explain that this is what you did in ninth grade. The average rate of change over an interval from A to B. And this would be from x equals A to x equals B, is what that means. So from A to B. So just imagine, if you would, go ahead and draw a picture right here in your notes. We're going to get a bigger piece of paper in just a second. But for right now, if you had a graph, and let's say the graph looked like this, let's call that function f, and that graph, let's say it continues on forever. And I wanted to find the average rate of change over an interval. And I have a point at A. There's x equals A. That point has an associated y value with it. What would you call that y value if this is function f? F of A. Yep, f of A. That was the right track. So you would call this f of A. Okay? And then if I'm going from A to B, let's say B is over here to the right of it, just because that seems to make things work out fairly nice. And there's another point on that graph, and it has a y value associated with it. For x equals b, what would be the associated y value? F of b. So there's that y value. And if I want to calculate the average rate of change over an interval, I can clearly see in this function that the slopes are not all the same. Okay, this function is not a straight line like it was in ninth grade. This line has a curve to it. And what that means is that the slopes are always changing. Well, I want to know what the average slope is. I want to know between these 2 points, what would the average slope be? What would the average rate of change be? Well, to find that, all you have to do is connect the dots. Find the slope of this line. And that would calculate the average rate of change. That would calculate the average slope. It would take all these slopes up and average them to give us an average slope. Okay, it's kind of like driving from here to the cities. Okay, I travel all kinds of speeds from here to the cities. But if I travel that distance from here to the cities, and I know how long it took to travel that distance from here to the cities, I can figure out what the average speed that I drove over that distance, even though I drove an infinite number of speeds between here and the city that were different. Okay, I wasn't always traveling the same speed until we're like, well, I got cruise control on. Cruise control ain't perfect. You think you're always traveling the same speed? What about when you go uphill, downhill? What about when you hit friction? What about when your computer or your car just sucks and the thing feels like it's going when it's in cruise control? It's never the same speed. Okay? Maybe you drive a nice Escalade and it's always the same speed, but my van definitely is not always the same speed when it's on cruise control. It's like, okay? So all those speeds averaged up to get an average speed. All those slopes averaged up to get an average slope. And it's real simple. You just take the points, the end points, and just figure out the slope of that line, and it'll give you the slope over that interval.
What if that line doesn't have an endpoint?
It will. It will for what we're doing. Okay, because in 9th grade, we always had to have at least how many points? We needed 2. So I'm going to give you 2 if I ask for the average. If I ask for average rate of change, you're going to have 2 points every time. Or they're going to give you the interval, and you're going to have to find the 2 points yourself. And that's pretty simple. If you want to find the 2 points, you just plug A in, and you get the f of A. You guys already told me that. And you get the f of B, and now you got your 2 points, which is A, comma, f of A. And then the other point would be B, comma, f of B. There's your 2 points, just like 9th grade. And you go f of B minus f of A. Sorry, f of B minus f of A. I did say that the first time. F of B minus f of A for the 3rd time, over B minus A, which is just rise over run, which is just y2 minus y1 over x2 minus x1. Thank you very much, 9th grade slope. All right? Nothing crazy, nothing special. You're like, okay, this is boring, let's move on. We already did this in 9th grade. If you make us do a bunch of slope problems again, I'm going to absolutely punch you, Mr. Morris. Okay? In my brain. All right? So there is average rate of change. Okay? So what I want to do is get to this formula now. I want to prove that this formula, what you did in 9th grade, is no different than the formula we're going to use in senior calculus, which is right here. So take your separate sheet of paper out. Let me get my separate sheet of paper out, because my paper's better than yours. Oh my gosh, look at that paper. There, that was crazy looking. It went all schizophrenic on me. All right, so here we go. So let's take and draw a nice big coordinate plane. That was not very good. That's good enough. And I want you to draw the curve, fairly decent size, about like I did. Let's kind of make it with a curve on it. We don't need multiple curves. Let's just get one curve on it. Okay, and this will be our first proof, and then we're going to work with this towards something new today, which is what we're going to call the instantaneous rate of change. But let's keep working with this average for a minute, and let's get this formula that I want to give you that's new and different. So what I want you to do is I want you to start with a point right here. It doesn't have to be exactly the same place as mine, but try and make it in the same vicinity so we can all be kind of working on the same thing. All right, and that point has an x value with it. So let's just call that generic x, because I want to create a formula that calculates the slope based on any x. It'll calculate the slope for any x value, because remember, the slopes of this curve are always changing. And eventually what I want to be able to do is actually calculate the slope at any one of these points. But before I can do that, I need to be able to write the average rate of change in terms of any x value, instead of picking out 2 specific points and calculating the slope. Okay? So what I'm going to do is I'm going to have this x value right here, and associated with that x value is a y value, which we will call f of x. Very generic so far. But now I want to calculate the average rate of change of between 2 points, but I'm not going to know where that second point is. We're just going to say it's a certain distance away from x. It could be any distance away from x. So now I'm going to define this second point in terms of this first point. You ready? I'm going to define the second point in terms of the first based on a certain distance away from that point. And we're going to call that distance away. I'm just going to travel a certain distance away to the right. It doesn't have to be the right, it could be the left, but it makes a little bit more sense when you do everything positive. And let's call that delta x. Now that delta x value, that's going to be the distance to the second point that I'm going to use. That delta x can also be called h. And the textbooks use both. So don't get scared by delta x. It can be called delta x or it can be called h. Some books use delta x, some books use h. Our orange book uses h all the time.
Yeah, but is it h used for height and stuff too though?
It is in physics, but h in this situation is used for a distance, which is kind of like a height. Okay? So, delta x or h. Now, if this is point x and we're going to travel a certain distance away from point x, what would this new point be called? X plus h or x plus delta x. So let's go with x plus delta x. The reason I use delta x first is because most college professors use delta x. If I get you used to that one first, nobody has a problem with h. So everybody has a problem with delta x. I try and get you used to the one you don't like first. And then when you go to the one you like better, it's like, well, the delta x is not that big of a deal. Kind of look at it no differently than you would look at the h. Now, this has an associated point with it, so project up to the graph, find that point, and then tell me what that y value would be. That would just be plugging into the function, f of x plus delta x. Very good. Now, we have 2 points, and those 2 points have coordinates. This first point has the coordinates x, comma, f of x. And this point has the coordinates x plus delta x, comma, f of x plus delta x. Is everybody okay with that? Now, let's imagine the slope of that line that passes through those 2 points. I'm going to draw a line that passes through those 2 points. There's the line that passes through those 2 points. That line has a special name from geometry. When you have a line that intersects a function in at least 2 points, it's called the secant line. Now, the reason I say at least 2 points is because it possibly could cross in more than 2 points, because we know functions can get really curvy and they can actually come back down and cross it again, like a sine graph or a cosine graph or a polynomial function like x to the third or x to the fourth. So it is very possible that this function might come down and cross it again. But I'm interested in really the secant line that goes through these 2 points. So a lot of times we won't even talk about the secant line, we'll just talk about the secant segment that passes through those 2 particular points. But here's the deal. That secant line is a measurement of the average rate of change from this x value to this x value. So it's calculating average rate of change. I mean, that's what a slope is. That's what the slope of a line is. It's an average rate of change. And it's calculating the average rate of change over this interval from x to x plus delta x. No different than from a to b. What we just did a minute ago, what we did in 9th grade. Now, let's actually calculate it with these new points, though, where everything is determined, or everything is in terms of x, some generic x value. So it's true for all x values. So it doesn't matter what 2 points we're talking about. We could pick any 2 points on that graph, and it would hold true for that. Okay? So, the slope, and we're going to call this now, we're not just going to call it slope, but we're going to call it slope of the secant line. Just put it in lowercase, slope of the secant line. All right, let's do it like we did in 9th grade. y2 minus y1. What would the y2 value be? F of x plus delta x. Minus, what would the y1 value be? Just f of x, right? All over x2, which is x plus delta x. We're going to have a da-da moment here in the denominator, okay? Get ready. So there's my x2 value minus my x1 value, which is just x. What's going to happen on bottom? X are going to cancel, and you're going to end up with what? Which is kind of a da-ha moment because we already know delta x is the distance between x and x plus delta x. So it should make sense that the x's cancel and we're left with delta x. So this is what we end up with. We end up with this formula, which, guys, this formula does the same thing. It does the exact same thing your 9th grade formula did. But now it's in terms of x instead of talking about 2 specific points in calculating the slope. It's talking about the slope in terms of x. It's talking about the slope algebraically. It's talking about our 9th grade slope in terms of a variable. Okay, and that's a benefit to us. Okay, it doesn't seem like it right now because it seems like, why don't we just find the slope? Why don't we just use numbers again and just find slope? Because that's not what I'm really after, okay? We already know how to do that. We're after something more, and that's where I want to take you today. I want to take you to that something more, which is instantaneous rate of change. And this formula is going to help us get there. You need to memorize this. This calculates the average rate of change, and this is a lot of times called the difference quotient, okay? I really don't care if you know the terminology. I just want you to memorize the dumb thing. F of x plus delta x minus fx over delta x. Okay? Can I take you to the next step? All right, let's go to a step further. Let's take this same picture. Can I erase? There might be a benefit to actually duplicate this graph, but it's kind of up to you. All right, so now let's imagine. I want to talk about the difference between average rate of change and instantaneous rate of change now. Okay? Average rate of change will only tell you what you're averaging over an interval time. It only talks about what the rate of change is over a duration of time, okay, or a certain interval, all right? Now we want to go to instantaneous rate of change. What's the difference between, what comes to mind when I say instantaneous rate of change versus average rate of change? Yeah, how fast you're going at that moment in time. And not just fast, because I'm not just talking about speed and velocity here, but I'm just talking about anything. It could be money. Maybe how much money Bill Gates is making at a particular moment in time, like right now. Boom. If I could ask Bill Gates, how much did you make right now? He could tell us, okay? Or he might not be able to tell us, but is there a way to do that is the question. Okay? Or if we went to the bank, could I know how much money I'm making right now? Like right now in that stock. Could I know right now at that moment, how much money did I gain in that moment? Or how much money did I lose in that moment? Could I find the slope at that exact moment? That's what I'm after. Okay? By the way, Bill Gates' money fluctuates like it's between $2 and $16 million a second. It's a very like, that's so much. Not when you're worth $77 billion. $1 billion is not a lot anymore. Okay? The definition of how much $1 billion's worth when you become a billionaire is like, okay, used to be a millionaire. Yeah, whatever. That's like pennies to him now. If you actually understood how much different it is between a million and a billion, I think I did that exercise with you when I showed you how much bigger a billion was than a million, right? A million second ago was like 12 days ago. Did I do that with you guys?
Yeah.
And like a billion seconds ago is like 33 years ago. And then you go to a trillion and you're like 25,000 years ago. Okay, so you get the feeling of how much bigger numbers are to each other. But so I want to know today, how do I find, I'm not interested in the slope of the secant line anymore. I'm interested, maybe on this curve, I want to know how fast you're going right there. Or maybe, do this. I want to know how fast you're going right there. Maybe I want to know how fast you're going right there. I want to know how fast you're going right there. I want to know how fast you're going right there. But here's the deal. What do you notice about the rates of change? The slope. There's a slope at this point. There's a slope at this point. It has a certain steepness to it. There's a slope at this point. There's a slope at this point. There's a slope at this point. And it's always changing. It's never the same. So how are we going to find that slope? Now, when we talk about the slope at a specific point, it's no longer called the slope of the secant line. When I talk about the slope at a particular point, we actually refer to it as the line that passes through that point, and if it touches that one point, and if I want to know the slope at that one point, this is no longer the slope of the secant line, it is called the slope of the tangent line. Okay? And a tangent line, if you remember from geometry, was a line that touched the circle at exactly one point. So we're going to talk about a line that touches the graph at exactly one point. Disregard the fact that the line might come back down and cross that tangent line. I know, guys, that if I keep extending this line out, that graph might come back down and cross that line. But we're talking about tangent at this point. So a lot of times we'll just talk about the little tangent segments. See, there's a tangent line here, 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 there's a tangent line there, there's a tangent line there, there's a tangent line. How many tangent lines are there? There's an infinite number of tangent lines. And I can find the tangent at every one of those points. And the tangent at any one of those points, if you calculate its slope, that's the rate of change at that point. That is what instantaneous rate of change is. It's like he said, look in your speedometer in your car at a given moment and say, this is how fast I'm driving at that moment in time. It's like if we watched Usain Bolt run, we took a picture of him and said, man, I wonder how fast he was going at that exact moment in time. Calculus allows you to do that. It allows you to figure that out. Think of it as like a cop holding the radar gun to figure out how fast you're going at a given moment in time. Calculus allows us to do that. Okay? On paper, precisely. Now in the real world, we know it's not as perfect. Whenever you go from the theoretical to the experimental, it gets a little messy on the experimental side. Okay? We can do all the theory over here in math. We won't make everything work out perfectly. But as soon as we go to the real world, things are going to have an amount of error to it. Would you agree with that? Okay, can I get an amen? Yes, there's going to be some error to things we do in the real world. It's not all going to be perfect. Okay? So let's actually calculate now and show you how this formula works. Okay? So we're going to go and talk about the slope of the tangent line. Now I'm going to do this picture first for you. And my picture is awesome. But then I'm going to show you the animation for this, and you're actually going to look at my picture and say, man, that was just stick figures and crap. Okay? It's going to be so terrible compared to what I'm going to show you in a second in the animation. But I like working through it with students first, because you get a good grasp on it. And then when I show you the animation, you're just like, oh, cool, I just know what we did. All right?
Should we take a copy of what you're doing?
I think I got it pretty enough, but did you write a bunch of crap on it? Then you're probably okay. So what I want to imagine here is I want to say, all right, Sir Isaac Newton was actually the guy that started contemplating this, and at the time that he contemplated, another guy in a different part of the world named George Leibniz, and they are both credited as the fathers of calculus. Two guys lived at about the same time. Okay, they didn't have the same birthdays or anything, but they lived at the same time period. Both were alive at the same time. And they both discovered calculus at the same time. They pondered the same question. And mathematicians and physicists were kind of pondering this question around the world. But these two guys pondered the question the right way and came at it at the right approach. And both discovered calculus at the same time. And they were in different parts of the world. Now, some people like to say it's a conspiracy. Some people say, well, he corresponded with somebody and stole it, blah, blah, blah. I'm not into the whole conspiracy theory. I'm just going to give them both credit because I really don't care. All right, so if you like George Leibniz better, you discovered calculus, go for you. I like Isaac Newton better because he liked apples, I don't know why. So he was a Mac guy. All right? So he would have had an iPod at the time. Okay? It'd have been on a little slate or something, I don't know. But click to the next track. I don't know. All right, so what he did is he said, man, I want to find the slope at an exact point. So let's just look at this point right here. It seems to be a really cool point. So I want you to imagine the tangent line at this point right here at x f of x. So there's my tangent line. He said, I want to know the slope at that point. I don't want the average. The average is great, but it's not like out of this world awesome. Okay, and I'm sure he said it like that. He's like, man, that's good. It's good to know the average, but I want to know what's happening at a specific moment. I want to know what's happening at that exact moment. So at that point, can I calculate the slope? The problem was he knew, based on all the math done previous to that time, that how many points do you need to calculate the slope? You needed 2. The problem was, if you got a tangent line, you only have how many points? You've only got 1 point on that graph. You've got the point that line has in common with the graph of that function. So he said, well, gosh, how am I going to calculate slope if I only got 1 point? So this is what he did. He says, you know what? I can at least approximate the tangent line slope, by using a secant line. So what he did is he chose a secant line relatively close, because we like closeness, right? Think limits here, guys. Think limit. He thought of a point. He said, I'm just going to choose a point a certain distance away, make it fairly close, and I'm going to start choosing secant lines that would. So he first of all started with one secant line. He said, okay, here's the secant line. Does it look like that secant line has a fairly similar slope to the slope of our tangent line? Fairly similar. Would you say good similar or bad similar?
Decent.
Decent, not so decent, right? It's an approximation, but I don't think it's a great approximation. So what he said is, you know what? I think I can get a better approximation. So I'm going to imagine a point a little bit closer. And I'm going to draw a secant line through that point. And I'm going to say that secant line approximates it better than the secant line before. He said, well, that's not good enough. I can get closer. So he chose another secant line. So he imagined a secant line even closer. And he says, well, that secant line approximates better than the secant line before, and it's getting closer and closer to almost resembling the tangent line. And so what he did is he kept taking points. And if you can imagine, if I draw a point, I'll take a blue one. Let's take blue. There we go. So he says, okay, I've got this original secant line. And if I just keep taking points and I move along that graph and keep moving the secant line closer and closer and closer, what's going to happen is that secant line is going to approximate that tangent line slope better and better. And how close do we want to get when we do limits? As close as we can get. How close can you get? As close as you want to get. You can keep getting closer. You can go you can go 0.001 close. You can go 0.00001 close. You can go 0.00001 close. And what he realized through the limit process is that eventually you're going to get to a point that you know, even though you can't calculate the slope of that tangent line, you know what it's approaching. You're going to get to the point where you say, oh, I think it's approaching in half. And you're going to be convinced, just like we were convinced last chapter, that once we get close enough is good enough, and we'll be able to say this is what it is with confidence. We'll know this is what the slope of that line is going to be, even though we can't calculate the slope of that line. Just like if I kidnapped Canyon, and I drove from the Fargo, and all of a sudden I drove up to the Walmart parking lot. Kenyon's going to be like, oh, sweet, Mr. Morris is taking me to Walmart. I don't know why, but we're going to Walmart because we're in the Walmart parking lot. Or if I took Ken and I drove up to Billy's house and I pulled into Billy's driveway, Ken's going to be like, sweet, we're going to Billy's house. I don't know why, but we're going to Billy's house because we're in this parking lot. And I don't have to be in the house to know we're going to Billy's house because we're close. Okay? Or whatever. Ken's parking lot. He put up a parking lot. Anyways. Alright, so you get to a point where close is close enough. And that's the idea I want you to get here, is that really the way we're going to go about this is we're going to take secant lines and we're going to let those secant lines get closer and closer to what? Tangent line. Eventually to where it gets so close that it resembles what? In fact, it will converge on the tangent line. It's almost like they're the same point. We'll get so close. And we'll get so close that we'll just be like, yeah, 0.499999999999999999999. 0.49, or wait, that would be a good one. How about yeah, I don't know where I'm going with this. Yeah, 0.4999999. What would that be? You'd say 0.5. You'd say 0.499, 0.49999, 0.4999999. It seems like it's going to 0.5. I think I'm going to guess 0.5. Okay? So that's what we're after here. Now, if this is happening, here's where we go. Here's where we go to the formula now. If this is happening, what is delta x doing as I keep taking secant lines and doing it better? As I get closer, and as I choose a point closer, and as I get better and better approximations for the secant line, for the tangent line based on the secant line, what's happening to delta x the whole time? Delta x is approaching 0. That guy will approach 0. So what happens is the slope of the tangent line really is based off the slope of the secant line. The slope of the secant line was this. You got it memorized already, right? I do. So if I take the slope of the secant line and I allow delta x to do what? So if I take the limit as delta x approaches 0 of f of x plus delta x, minus f of x over delta x. You kind of look at it and you're like, okay, well, if I let delta x approach 0, this is no longer the secant line. If I let delta x approach 0, that secant line is actually going to converge onto the what? Tangent line. So now, this formula, just by throwing the limit in front of it, is no longer the slope of the secant line. This is now the slope of the what? That right there calculates the slope of the tangent line. Crazy, isn't it? We got a name for it. In calculus, we call this instantaneous rate of change. Instantaneous rate of change, which we also refer to as a derivative. We call it the derivative of a function. Now, this is the thing I want you to know about this, because we use the formula f of x plus delta x minus fx over delta x. This slope of the tangent line is not just for one point. This slope of the tangent line formula that we just came up with will calculate the slope of the tangent line for any point on that graph. That's really important that we make that distinction. It doesn't calculate a specific point. It'll calculate the slope of the tangent line at any point. And you're going to say, well, how might it do that? Well, I'm going to show you. Okay, but before I do that, I want to show you my little animation. Okay, so here's my animation. Where'd it go? There it is. Let's reset this guy. Now, my picture is just going to get annihilated because this is like the perfect picture. Okay, first of all, I've got a polynomial function up here, ax to the fourth plus bx cubed plus cx squared plus dx plus e. And you've got a, b, c, and d are the coefficients. And based on the coefficients, you can kind of change the polynomial. Right now, a is 0, because these are sliders down here. A is 0. And so it's actually a cubic function because there is no, if a is 0, there's no x to the fourth term. You get that? So that's why it's up to the right, down to the left. And I can actually slide that around. So if you want to see it, just what I mean by that, like I can change a, look. So now it's x to the fourth. That's why, so I'm going to go back to 0 though. So there's back to 0. And you can change it and make it all kinds of different polynomials. So, what I want to imagine, if I want point P, and I want to find the slope at that point, it looks like it has what would you guess? Anybody want to take a guess at the slope? Let's play guess the slope game.
Like 1, 2,
What do you want to say? Slope of 1/3. So 0.3, say? Anybody else going to take a guess? You can guess because he's wrong. Okay, 1/5, he's wrong too.
1/2.
1/2's getting closer. You could get, here's the point. Could we get it exact? No, we could just estimate what we think it is, right? The thing that I'm encouraged by is you guys know it's not very steep, so like 1/2, 1/3, 1/5, you're guessing slopes that aren't very steep, so that's on the right track, and you're guessing positive slopes. If anybody said a negative slope, I would send you out of the room for timeout, okay? All right, so let's go ahead and look at it. The slope was actually 0.450. Very close. Not that close. All right, but 0.450 is the slope, and it calculated it for us, okay? But we want to see how you can actually get that on paper. How would you actually do that? How would you work that out? Because we only have one point, and this computer measured it for us. Okay, so how can I actually work that out? Well, here's what you do. You do like Isaac Newton did. You say, okay, I'm going to imagine another point a certain distance away from x, and we'll call that certain distance away from x, h, or delta x. And then I'm going to plot that point. We'll call it point Q. And that point Q has coordinates x plus h and f of x plus h, just like Mr. Morse did, but this picture's a lot better. And now we'll create the secant at that through point P and point Q. So now we have a secant line. And just like Newton did, we're going to say, okay, well, that's a decent approximation for the slope of the tangent line. But I can get a better approximation by just letting h approach 0. So I'm going to approximate. Well, I'm going to stop there just a second. Is that a better approximation than before? And then I can hit it again. Is that a better approximation before? Really, how close do we want to get, though? As close as possible. So we're going to play the game of how close can Mr. Morse get. Billy saw the record. The slope is 0.450. I got 0.452. So let's see how close I can Yeah, I totally missed it. I went around the horn. By the way, is the secant line approaching the tangent line? Okay, here we go. Gotta be on my game. I know I can't go any faster. I'm gonna try, but last time I did went right by it because I got to .456 one time. No, okay. Yeah, just not happening. But anyways, you get the idea that it is approaching that tangent line. Eventually gets so close that it actually resembles what? You actually think it becomes what? Now we know physically that can't happen because we actually can't get to, that distance. We can always have a distance that we can get smaller. We know physically that can't happen, but theoretically it can happen. And we can just say we know that it's approaching .450 for a slope. You can actually show it from the left as well. So you don't have to do it from the other side. If, maybe Leibniz did it from the left and Newton did it from the right. Okay. I don't know, one southpaw, I guess. And then h equals 0. Just show you what would happen if you actually let h approach 0. Obviously, there you see that nothing will move because the button's already pushed. Thank you very much. All right, so then you see that the slope of the secant line is actually the slope of the tangent line now. The definition of derivative, again, there it is. And it is calculating the slope of the tangent line, not at that point, but every point. Okay, I know I've got that point drawn there, but remember that point's in terms of x, so really that point could be anywhere. I can move point P anywhere and it's still going to be the same thing. Okay, and then we calculate the slope of that particular point. So get the idea? All right, so we're going to do a couple examples here. So go back to your notes. Let me pause this video for station.